open the PowerPoint to full screen, it comes on blocks the screencast-o-matic, and then I can't open it. Then I have to close things down and open them back again. So I think I'm on the right slide here. So let me get this opened.
Will we be using the book today, or are we waiting to use the book?
Always using the book. So, the slide set goes pretty much through it. So if you got your book, was this Brianna talking or was this
Brianna, it's
Brianna?
Brianna.
Yeah, well, you got your book, so it's good that you have it.
Okay.
All right. Um, we're going to pick up where we left off last time and move on from there. Do y'all have any questions, issues, concerns, problems that you want to address before we get going? Brianna had mentioned that she's having some Microsoft problems, but not much I can do with that, but I hope you get them settled.
When do we start doing labs?
Today at 5:45. Okay, so
Okay.
don't let me run over. Okay, 5:45 we stop class and start lab.
Yes, sir.
Okay, now um, I do want to say this about a little bit of an update. We got a fair amount covered in chapter 1 on Tuesday, a little bit more than probably I was expecting. So I went back into your weekly activity type thing and put chapter 2 PowerPoint in there as well. The odds are we will get started on chapter 2 today. Now we're probably not get too far into it, but we will get started on it, and then we'll go from there. Also, after we finish today, we'll have class from now until 5:45, and then at 5:45 we'll start the lab. We'll have the lab. Uh-oh, my internet connection is unstable, so I'm going to not talk anything. Okay, did I break up some in there?
Yeah.
Okay.
Yes, sir. You
I
did.
got a little flash that came up and said my internet connection was unstable, which is really interesting because last time I checked, I think I had 5 bars. So it's something beyond the connection. I believe it's the whole system gets swamped. But anyway, I was just going to say we will go from now until 5:45 for class. Probably finish chapter 1 in that time. Get started in chapter 2, but wherever we are at 5:45, stop there, and then we'll move to the first lab. Now, I think I was also saying, so therefore on the first week's activities, I went in and put in the chapter 2 PowerPoints too, in case any of you want to pull those up. Unfortunately, I didn't have much time until recently to do that. So, and then I put in a little bit more that we'll be doing, probably covering chapter 2. Um, the lab today will involve both a link, a web link, and I'll show you where that is, and also a Word document that I posted there too. And those are right on the same place, and I'll show you where they are when it's time for lab today. Then we'll work on lab, and more than likely we'll finish the lab well before the 2 hours are over with. And to keep from cheating you out of your tuition dollars, I'll just ask your opinion whether you want to go on and end early if we can do that, or if you want to go back to chapter 2. I just right now know which one you're going to say, but we may end early instead. Okay, never mind. Just kidding. Um,
Question, Mr. Fowler.
yes,
So, are we doing labs every Thursday?
we'll be doing labs more frequently than every Thursday. Like I said, if we get started in chapter 2 today, the odds are we'll get far enough along in chapter 2 on Tuesday that we'll be doing lab on Tuesday as well. We didn't do a lab the first Tuesday because I had all the stuff about, whoa, here comes someone coming in. Gerald's here. Okay, let me get Gerald in here and marked here if I can find his roll sheet. So Gerald is here. All right, top part of the alphabet's coming in pretty strong here, and the middle is doing fairly well. The last part of the alphabet is lagging a bit today. Okay, So hopefully more will be coming in. But yeah, we're going to have, okay, now who was it that asked the question? Leon? Is that right?
Oh, yes.
Okay. If it was you, let's see, you had Physical Science 1 in the summer, is that right?
Yes, that is correct.
Okay, in the summer, we had, supposed to have had, what was it, 10 weeks. We didn't really have 10 weeks, but we had more than 8 weeks. Well, this Physical Science 2 has more labs but fewer tests. So we'll be doing more frequent labs but less frequent tests. Now, the first test is coming up pretty quickly, but the second test, we'll probably have 3 labs before we do the second test. Okay, so we'll move at a slightly different pace as we did last summer, but it'll still be moving along pretty rapidly.
Okay. So before we do the lab, are you gonna break down like what we have to do, like in that lab?
Right, well, I've already sent you the materials. I'll be showing you the PowerPoint, and I'll actually be running the simulation. Now, the reason I'm doing that is not everyone, or at least this is my experience last spring when I taught this course, when we had to leave campus and then had to start doing virtual labs, students had trouble accessing all the virtual labs we had. I don't know if y'all are going to have that problem or not. That may have been because we're just getting going. It may have been because I don't know what the reason was, but they said it was something to do with oh, what is it? Some sort of Java scripts and things like this, that not everyone had that on there, and they were required for the labs. So if you can't open the simulation, you'll still be able to watch me do the simulation. And like I said, we are recording right now. We'll record all the classes and all the labs. So therefore, even if you cannot open the labs, you can follow along in class and do all you can with that. If you miss something, you can go back to the YouTube videos and pick that up. Now let me say this about the YouTube videos. On Tuesday, at the end of the day, which was probably a little after 10 o'clock at night, the YouTube video had loaded, it said, but I couldn't move it to the playlist because it got into YouTube but hadn't been sorted by YouTube, so it wasn't showing up on my screen. So then it was Wednesday that I was able to finish loading it, but something happened there, and later in the day it still wasn't done, so I went on. So it was later on Wednesday than I hoped. Hopefully today's class will be there fairly soon. I'm going to say I should be able to get it out there tomorrow morning. Okay, it probably won't be ready today because there's going to be a lot of stuff in today's class, but then probably it'll be out there tomorrow morning, and tomorrow morning I'll load it on the playlist. So anytime after that, you'll be able to go back and review anything about the lab or the class, because this right now is being recorded. Okay, was that an adequate answer to your question, or was that not even what you were asking about? I believe it was Angelita, or was it Brianna? Who? Okay, it must have been Angelita. So,
Are you talking about the lab?
yeah, did that answer your question? Okay.
Yeah.
All right. Okay, now, before we get started today, and I hate that I have to take the time to say this and do it, but it's just sort of to explain a little bit of what's going on here. Several things have happened. This week has been a weird week, and I wanted to share with you a little bit about what may be coming. And I'll start with my personal situation. As I think I told y'all before, I have a mild form of leukemia. It's called chronic lymphocytic leukemia. I've had it since 1991, probably before most of you were born. So it's not a real aggressive or anything else, but I've been receiving, actually the first 17 years after they discovered it, they said, look, the treatment is worse than the cure. I'm sorry, the treatment is worse than the disease. So they said, as long as you can hold out and not being having any adverse effects from it, just we'll keep monitoring your counts. So they did for 17 years. Then the counts got high enough that finally, Angelita got bumped out and then came back in. They got high enough they did have to start a treatment. I think I went through this last time. Because I had just gotten off the video chat with the doctor then. So basically what the bottom line is now, I had to go in for more blood work yesterday morning because they want to make sure that the drug they're treating me with is a monoclonal antibody that is the best thing, the best one to attack the disease as it is now. As it was a few years ago, it was the best, but they want to make sure the disease hasn't mutated somehow so it's now resisting this. All indications are it's not. The odds are I'm still going to have that treatment, okay? But he wanted to make sure. And also, I'm very anemic right now, and I got this way after the treatment I had in January, and I'm that way then now. The bad news is this is before a treatment, not after a treatment. That one was after a treatment. Someone just came in and I couldn't make out his name. So let me see who that is coming in. I thought it would hang up there a while, but it didn't. There, it's Drede, okay? I'm wondering if that's Drishon. That's the closest I have for that. Is that who's come in? He still doesn't have a microphone on. Can I find out who Drede is? Drede with 3 boxes after it. Okay. What I see is you don't have a camera on, but I don't even have an icon for a microphone. So, Drede, can you let me know who you are? Are you still trying to connect to audio? Let me see if I can find out this way. Yeah, connecting to audio, so he can't even hear me yet. Okay.
Yeah, sometimes like when we're coming in, like it gives us like an option to like use like calling internet audio or dial in or whatever.
Okay. Well, his connecting to audio turned off, now it's on, then back off again. So Drede, can you hear me yet?
Yes.
Okay, who are you? Are you Drishon Wilson?
Yes.
Oh, okay. What do you go by?
You can call me Dre, son.
Say that again.
You can just call me Dre.
Dre? Is that what you said?
Yes.
I'm hard of hearing, so it's hard to hear. Okay, Dre. As in D-R-E-Y?
No, just D-R-E.
D-R-E, got it. That's what I thought maybe you meant. Okay. So this is your first day in the class, right?
Yes, sir.
Okay.
Yes.
Now, because of that, it was also Leon's first day in, but he was in the class this summer, so I wasn't as worried about him. But because it is your first day, what I'm going to do is take you fairly quickly. Okay, are you familiar with the new Blackboard templates that we're using? Are you in other classes?
Yes.
You are, okay. All right. Let me take you through just a few of the issues that are probably different for this class than they are most of the others. So I'm going to go to a new share here. I'm going to go to probably this one. Yeah, that's it. Okay. And you can see my Blackboard, not quite home page, but something like that. Okay, here's this class. Well, it was there and then it slipped down. Let me get it back up so you can see. Here's the class right here. Now, is this more people coming in? I don't see them. Let me see. And this will be also for you, Leon, because they instituted this template this term. So this is, to me, a lot harder to follow. And I think their whole thing was to make it easier. But boy, did they ever fail on that one. I got to scoot Jacob over and some of the rest of you over there. Okay, now I'm going to close this out. You can't see it, but it's blocking my view. And I'm going to move you folks, you can't see this either, but up there, so you're kind of out of the way. Okay, not that you're ever in the way. Okay, the thing about starting here, okay, this is for mostly for online classes, not necessarily. Let's see, is someone else trying to get in? Let me see if they are. Yes, two more people. Okay, Tobias and Diana. So let me get both of them here. And as soon as Tobias gets here, I'll find out what he likes to go by, and also Diana to see what she likes to go by. So can either one of you hear me yet? Diana or Tobias?
Yes.
Okay, Diana, I know what you go by. Okay, sorry about that. How about it, is it Tobias A. Williams Moss? Okay, what do you like to go by?
Mr. Brown.
Yeah, Tobias, okay. What'd you say? Somebody said something.
I was gonna ask something. So you know how we had physics 111? So is it physical science 111? So are we gonna have is physical science 112 separately than that?
Yeah, it's a separate course. Same textbook, but separate course. The okay, the 111 was basically, and it's over with now. Okay, I can't remember if you got everything in. I think you had, but okay, it was astronomy, earth sciences, which included weather and climate and oceanography, or Earth's waters. Okay.
So do you know how long this one's gonna last till? Like December?
Yes, it'll go right till December when all the other classes end. They're both 8-week terms, okay, mini terms. You finish the first 8 weeks, we started the second 8 weeks, and we'll go right up into the last term of class, and that's when it'll be over. Okay. Now, so let me head back to, was there another question, or was that all? Okay, I was going to say the Physical Science 112 covers physics and chemistry. The other covered astronomy, geology, meteorology, oceanography, those kind of things. This class covers physics and chemistry. Mostly physics, some chemistry. Okay? Yeah.
Sorry, I have one question. I understand that you were given like extra like bonus points on the research paper if we turn it in, like if we turn in this month we get like 2 extra points.
Right.
Other than that, do you offer any other like extra credit work, or is that it?
Well, that's it. I do drop your lowest test score and your lowest lab score, which is sort of bonus, but no.
That's the only thing.
Okay, yeah. Because, hey, and who is talking now? Is this
It was Brianna. I was
Brianna? Yeah, well, I think you probably came out of 111 pretty well, didn't you? I don't think you needed any.
Take 111. I took it.
Oh, no, I'm sorry. That's right. You're in my math class. You're not in this class. Yeah. But yeah, you'll find this is even easier than the math class, and you're breezing through that, right?
Yeah.
Yeah, okay. Say it with more enthusiasm.
You're gonna do well in physical science. It's pretty straightforward.
Oh yeah, I mean I'm good with all my other subjects. It's just that math though, that's always been my worst subject. So
Okay. Yeah. You won't need any bonus type stuff here. Okay. That's what Angelita, I think, was trying to say. Okay. And yeah. And she's saying it's way too easy of a course. Isn't that what you were saying, Angelita? Yeah.
It's not.
Okay. So let me, for those who are new to this course, and several of you are to this course, so let me, and you weren't here the last time, let me go over just a few of the highlights that are different for this course than probably some of your others. Now, all of them say start here, and this is that whole thing about online courses, and it's way more for online classes is for us, okay? But included here is the course syllabus. That's where you'll find it, okay? This course syllabus agreement, they talk about this all the time. You can go through the method they show you here, or you can just take a picture of it and send it to me. You can do anything you want to. The thing is, you folks are here. You don't need it for your attendance because you're here. But the people who are not here, and let me just call off the names of those so far. Still haven't seen Gerald Jordan, so if any of you know him, please let him know he needs to do this student course, course syllabus agreement. If he doesn't do it, they kick him out of the class. Thomas Habrowski, he was here in the summer, but I haven't seen him yet this term. So if you know him, if you have a way to get in touch with him, tell him if he doesn't get this done, he may get removed from the class. Sharonica Ruffin, okay, it seems like she was in one of my classes before, but I don't know that she ever showed up for the class. So she needs to do the same thing. And then all the rest of you are either here now or you were here on Tuesday. You don't have to worry about getting kicked out of the class. You've already established your attendance. It's the people who are not here, they've got to do this course syllabus agreement. Everybody's supposed to do it, so please do it. But the people who are not here, that's the only way I can mark them present for the week. Okay. The textbook is... That's the Tuesday and Thursday class from 3:15 until 7:45 in the evening. So it's a long one, okay, because it's mini-term with a lab. Okay. There is the textbook there, the American with Disabilities, okay, ADA. So I'm going to scoot back to the top here. That's what's under Start Now, okay. The next is the instructor contact and office hours. And this in here twice, okay, right here. It says preferred contact. I don't really like email, but that's the best way to get in touch with me, or Blackboard messages. Both of those are fine. My office hours, virtual office hours, I'm always here at home, Monday, Wednesday, 8 to 10 and 4 to 6, Tuesday, Thursday, 1 to 3 only, and Friday, 8 to noon. Now, what I was just about to say before we got into this, that impacts that a little bit. And here's what I was talking about my leukemia, okay? I'm going to need a treatment soon. We don't know when. They did the blood work yesterday. They said it'd take about 48 hours to get the results. So sometime either this evening or tomorrow morning, I'll probably get the results. Whether the doctor will tell me or not, I don't know. But they'll try to schedule me for a treatment. If I stay on the same treatment, because it's been more than 9 months since I had a treatment, that means they're going to have to do a 2-day thing. And this irritates me, but it does. They did that the very first time. I didn't have any problem with 10%, didn't have any problem with 90%, haven't had a single problem with it since, and I've had it several times. But because it's been 9 months, they want to go back to the 10%, 90%. They won't do it 1 week to the next week. They want to do it one day after another, which means most of the time I have my treatments on Friday, so I don't lose any class time. So the 90% will be on a Friday, which means the 10% will be on a Thursday. So it could be as early as next week I may have to go in for a treatment. This is still a maybe, okay? If I do, it depends on, number one, what time of day they set me up for, and number two, how long it takes. Now, I can't answer either one of those right now because I don't know. If they schedule me for the morning, there's a good chance I'll be home in time for 3:15 class. However, if they schedule me in the morning and it takes too long, I may be late for class. Okay. If they schedule me for afternoon, that means we'll probably lose most, if not all of the class. Maybe not all of it, but I don't know if y'all want to come back, say, after 5 o'clock or 4:30 or something like that. So there's a lot up in the air now. Hopefully by next Tuesday, I will know something. Okay? So that's number one, and that's the biggie. Now, whatever Thursday, Friday they do it, that means on that Friday, these office hours are no good because I'll be at the Kirkland Clinic. I can't really have office hours there. Usually the wireless signal is terrible there. Either I can't get on the computer or can't even get a cell phone service there. So the odds are, and then too, once they give me the Benadryl, it knocks me out. So I'm not any good anyway. So some Friday coming up soon, I will not have those office hours because I'll have to take a sick day that day. Another Friday coming up, probably in 2 weeks, I've got to be out of town because we've got business to take care of in Georgia. So we're going to have to go over there on that Friday. I'll let you know before that happens. Okay. So that's what I wanted to say there. Now let's see, was that someone else coming in, or it's just because I grazed I don't see anyone else coming in. All right, so let's move on to the next thing. Here's instructor contact information. It basically says the same thing it does here, just a little more detail. So you can read that to your heart's content. Okay, so that was that topic. I'm going to close that and go to the weekly assignments and activities. Okay, now we're in week 1. That's a good place to be. Okay, and let's open up week 1. And the first thing they show here is the overview and weekly to-do list. This is a lot of blah blah blah, so I'll open it up just to show it to you, but we won't go into gory detail on it. They make us do this. It's really, I feel like, fairly useless. This is what we're doing this week, the overview. These are the objectives for this week. That's the pretty much a summary type thing. And then what you have to do, read, blah, blah, blah. Okay. We will be doing the lab. Once we finish the lab, I'll probably be posting the test 1. Okay. And this stuff I added more recently, read and study chapter 2. Okay, so that's that. Look at that every week. Okay, to me it's not as important as this one is. Okay, instructional materials, lessons, PowerPoint, blah blah blah. Okay, I'll open that one. Here are the PowerPoints for chapter 1. We're right in the middle of that, maybe more than halfway through. Then the ones for chapter 2, I didn't have them in there before because I didn't know we'd get as far in chapter 1 as we did on Tuesday. Now, for those who missed Tuesday, you can go to this right here. This is recorded lectures. It's a YouTube playlist for this course. And I'll take you there real quickly because it usually opens up really fast. So just click on the link and here we are. Okay. Now I'm going to move you out of the way so you can probably see fine. I can't see it. Okay. Now, what you see at the top was the last time I taught the course, the videos from that. What you see at the bottom, and I'll scroll down to the bottom here, this was the one for last time. This was This was the whole class last time. 4 hours and 28 minutes of it. Okay, so if you weren't here last time and you want to see what you missed, there it is. I go over the syllabus, I go over Blackboard, I go over the research paper requirements, I go over my locator card, I go over everything I could think of to go over, and then we started in chapter 1. So if you want to get what you missed last time, there's where it is, the bottom. Now after today's class, that will go on the bottom, and then I'll probably take out whatever was on the top up here if it duplicated what we did do today. Okay, that's not all the way to, oh yeah, it is all the way to the top. This is chapter 3, 4. So this is not from last time, but a time before last. Somewhere down here, you'll see the one from last time. There is where it is. Physical Science 112, 1.1 to 2.2. That's probably going to duplicate today. Okay, then there's 2.2. If we get more than this, then I'll probably do that. That may have been 2 in this. I don't know why that was so long in that. But anyway, I'll remove the old and go to the new. Okay, and the new will be at the bottom, the older will be at the top. Okay, so that's the YouTube playlist. Now, every week it'll say recorded materials. I'll say go back to read week 1 and see the link there, rather than having to link to that every week. Okay, now handouts. This is the research paper instructions. Okay, everybody is required to do a research paper. I need to get your proposed research topic that a couple people have already talked about today. Get that to me sometime this week if possible. If not, next week is fine. You'll hear me talk about this on the class that we did on Tuesday. So go back to the YouTube playlist, go to the bottom of it, listen to that first class, and you'll hear me talk in gory detail about the research paper. So if you don't want to just read it, you want to hear me talk about it, go to the playlist. Locator card. Here it is in static form. You'll hear me talk about it up here in the recorded lecture. Okay, here's today's lab. We'll be coming back to this today. Here is a link that we'll go to. Some of you may be able to open it, some may not. I may have to load something to open it. I did last time. I don't know if I'll have to reload it again, but we'll get it done. And this is what you'll submit back to me. This is basically, I can't see myself, but maybe you can see this. There is the lab, front and back, okay? Or you can do it on 2 pages if you want to. That's the lab that we'll be doing today. And then the last thing here is the library services for physical science. We have one librarian that has been assigned specifically to cover not just this physical science class, but any of the physical sciences like physics and chemistry and this class and anything like that. And she has put together a pretty good listing of what services they have to offer. She may be a big help when you're trying to do the research paper. So take advantage of that. That's a link, a PDF form. Just click on this. Anytime you see the 3 dots, click on that. It says download the original file. If I clicked on that, then you'll see the file start downloading over here in the lower left corner. When it finishes downloading, click on it, it'll open up. I won't open it up now, but because it doesn't take too long, but we need to get on with class. So that was there. Okay, so overview, a lot of blah blah blah, instructional materials, a lot more useful stuff. Week 1 discussion. Okay, this is mostly for online courses, not for virtual classes. Okay, but if y'all want to get into a discussion with one another and with me on any topic we're hitting, let me know. Put it out there. Okay, send me an email and I will put out the discussion there, and y'all can feedback one to another. I'll try to be in on it some, as much as you like. Here's lab 1. Now I'm going to open this up just to show you. I showed you where lab 1 was here. Okay, here I would have put it here, except that whoever set up this template forgot to put a plus sign here. Without a plus sign, there's no way I can load it here. However, if you want to load your results and send it back to me this way, there is a way you can do that. I don't know how. I've never done it because I'm not a student, but if you can figure it out, if you're doing it in other classes, you can do that. Otherwise, just send me your lab as an attachment to an email, as an attachment to a Blackboard messages. Either one of those will be fine, or through this site right here. I check all 3. Okay, so you won't find lab 1 here, but you can send me back lab 1 here if you choose, or you can send it by email or Blackboard message. Any one of the 3. Okay. Now, week 1 assessment. Okay. I'm going to open this up to show you. Again, whoever did the template forgot to put a plus here. So I'm going to label this when I put the test out there. I'll say test 1 or chapter 1 test or something like that. However, I won't be able to load it here. I'm going to load it through Blackboard messages. Okay. And I'll show you that in just a couple of minutes. If they had done this correctly, I could load it here. They haven't. Okay. So I'll get over this. But you can send it back this way or send it back through an email message or a Blackboard message. Okay. And this shows how to submit an assignment on Blackboard, so if you want to do that. Week 2 hasn't been set up yet. I'll set that up sometime over the weekend or possibly Monday. Okay, hopefully I'll have it at latest Tuesday Tuesday early afternoon before class. Okay, so there is pretty much it. Now here's one more thing, and this is for everybody. Something I forgot. Oh, I didn't mean to get out of that. Let me go back in here. I meant to just get out of the weekly assignment, but it's closed now. One more thing I forgot last time is right here. Now Gerald's in the way again, so I've got to move him out of the way. There we go. To open this one, click on the down arrow, live virtual class meeting information. And this was said back there under the course overview, the weekly overview. I say this every week, and it's also here. On the evening before each class, I will post on Blackboard announcements a Zoom invite which will enable you to access the next day's class. Obviously, all of you have done that because you're here. Here's the announcements right here, Blackboard announcements. Okay, I don't remember what the first one was. I think it was something about the NASA program. Okay. And then that's it until we go to final exam. You won't need anything any further here. See, these are the little pluses which enable me to do something else with it. That's what they left off of the template, so I can't put your things there. So now I'm going to move Tobias out of the way again, and we'll go back to the top here. And this is where we are now, course content. This is calendar. I don't use that. If you want to use it, you certainly can. This is discussion. I think that has to do with the discussion groups. If we have them, let me know. I'll try to facilitate that. If you don't want them, no sweat. This is the grade book. Nothing in there yet. Well, I can't think if there's anything in there yet, but that's where your stuff will start going once you start turning things in. Then this is the one right here that's the Blackboard messages. Okay, and I doubt if anything's there yet. Oh, there are some things yet. So Amia, I think is her name, she sent me this about an hour ago. Valerie sent me something. Dre must have just come back in. And Dewan Horn says his week 1 agreement isn't opening. So at least I've heard from all these people. Amia was here last time, and so was Valerie. Dewan, I will try to get him marked on the thing that he has gotten in touch with me. The trouble is, Dewan Horn is not on my roll sheet. So maybe he's added since the first day of class. I'll have to check on that. Okay, so I don't know who he is. This next one here is analytics. I don't use that, so if you have anything. But this Blackboard messages, that's where I'll load your test. If I can't get it on the weekly activities, or even if I do put it on weekly activities, since this week I've got to put it there, I'll put your test there as well. The labs, though, they're going to be on the weekly instructional materials. That's where they'll be, and then they'll have another icon under weekly activities that you can send them back. And if I can put them there, I'll put them in both places. Okay, that's what this new fancy templates they just have so much redundancy, it's hard to remember where anything is. So I try to put it every place I can. Okay. Now, any questions, especially you new people or the older people, on any of this on Blackboard? All right. The book. Okay. Earlier, who was it? I think it was Brianna was showing the book. I can't see myself here. Let me see if I can find myself again here. There was an arrow that let me scroll up and down before, but it's not. Oh, there it is. Let's see if I can find myself. There I am.
Did you need to see the book?
No, I've got it now. Okay. I couldn't see my own picture. Okay, there's how the book looks. Physical Science, Bill W. Tillery. It's the 11th edition. It's a McGraw-Hill book. It is not a Cengage book, so it doesn't work under Cengage. But I think McGraw-Hill has something called Connect. So if you have any other courses you're in that you're using McGraw-Hill books, they may have something similar to Cengage Unlimited. I think it's called Connect. So you can look into that. Okay. Now, this is the big thick book. Okay, the full book. However, the bookstore, and now when I say that, it's the bookstore on the Bessemer campus, not the one on the Birmingham campus.
Well, the Birmingham campus did have a few.
Really?
That's
Okay.
where I got mine from.
Okay, did you get the little one or the big one?
This is the little thin paperback.
Okay, yeah, that's the little one, and that's the one just for this course, right?
But they only had like after I got mine, it was only like 4 or 3 left.
Right, okay. Those are much cheaper than the big book, but you can also order it online. You can order it from used book places. Even if you went to an earlier edition, like the 10th edition and stuff, the page numbers may not be the same, but they'll be close. But the content is basically the same. Physical Science hasn't changed in the last 2 or 3 years, okay? So it's good, okay. Good deal. Now, any other questions on Blackboard before I leave it? Okay. Now, the one other thing that I was going to bring up before we actually get started, sorry it's taking so long. I hope this won't interfere with class any, but since there is a possibility, I'm going to let you know this. A very good friend of mine died this morning, okay? She was a member of our Sunday school class, had been a member of that Sunday school class for probably 15 or 20 years, a really good friend. She was 76. I guess it was heart, pulmonary, something, but she collapsed on Tuesday evening, and that was after our class was over with. I found out about it, and then she was in the emergency room. They were stabilizing her. She went to intensive care, and then this morning she died. Okay, now, she has no family anywhere in the area. Last we heard, she had a sister in Virginia, but her sister was several years older than her, as few as 7, as many as 15. Well, that would put her very, very old. So, but they weren't in contact with each other. They basically, her sister had grown up and moved out before Judy was old enough to really know her well. So I'm in charge of just about everything to do with that, and periodically I'll be getting phone calls from the social worker, from the church, from someone. If I have to, I'm going to answer those. If I can get by without it, I won't. But if I interrupt class for something like that, it's because it's something that looks pretty urgent, okay? Because I've got to clear out her apartment. I've got to do all things because I'm in charge. I was the closest person she had here in Birmingham, so it's been a tough time, okay? So anyway, boy, this morning's class, after I heard about it, you talked about tough class. That was a hard one to teach, but sort of dealt with it. I found out I don't have to worry anything about funeral arrangements. She left her body to science. UAB is going to take it over, and they will not be through with it for several years, and then they'll ask where we want the ashes. So that's that takes a, not that it's an issue, but it does take a lot off. She wanted that to happen, and it is going to happen. So kind of good news, bad news situation, but that was what she wanted. And so she's getting her wish. So anyway, there's still lots of little details that will be coming up. So enough of that. Let's move on. For those who weren't here before, even those who were, we're in chapter 1. What is science? Sort of a nebulous little chapter at the beginning of the text. And we're on page 12. And they're giving what they call an example problem. Now they have examples scattered through the text, but this is part of the text that it says for an example problem. Okay? And I'm going to use this screen that says more math because I don't know why this is up here, but it is. But I'll try to work around that. So here's what they say. Use the equation from the previous section describing the variables at a fuel pump. And here was the thing that we didn't go over this thing, but that V, if I can get the pen to show, there it is. Okay, V is equal to TK. Now that doesn't make a lot of sense there. It says to predict how long it will take to fill an empty 80-liter tank. Well, I'll tell you what V is. V is volume. And I'll tell you something else. 80 liters is a volume. So that's the volume here. V is equal to 80 liters. That's what the V is. Okay? Now, T, little t, almost always is time. Okay? Very seldom will it be anything other than time. Capital T may be temperature. Little t is time. Now K is, remember we were talking about this last time, your proportionality constant. This is saying the volume of the tank is proportional to the time. Here's your proportionality constant K. And they say assume that K for this pump that you're using is 40 liters per minute. Now most of you can just look at those numbers and answer the question right there. Okay? But let's actually use the formula. Okay. Now I'm going to first do it the way the book recommends. Okay. The question is how long it will take to fill the tank. Now when they use the term how long, sometimes that means a length. That's not what they're talking about here. Now when they're saying how long, they mean how long time-wise. So how long will it take? So what we're looking for is the T. This is the unknown here. Now they say put things on the right hand side of the page, the left hand side. It doesn't matter to me. So what we want to do is solve for T. So how do we do that? We divide both sides of the equation by K. Isolate the T, the thing you're looking for. Here the K's go out because K over K is 1. And what we have is T is equal to V over K. Now plug in the values. Well, number one, make sure that your units make sense. Here the volume is in liters. There the volume's in liters. We don't need to do any conversion factors. We're perfectly okay. So we'll do V is, from down here, 80 liters. And from up here, the K is 40 liters per minute. Hang on to your units. They're your friends, okay? And you'll see why in just a minute. Now, I can do this math. 40 will go into 80 2 times. Liters cancel out because one's in the numerator and one's in the denominator. And what we're left is 2, the number 2, but then the units is 1 over 1 over minute. Now, if you remember how to do division of numbers, you do them with the units too. That would be 1 divided by, wait a minute, divided by 1 over minute. And that's supposed to be a minute, not a minute. Okay? Well, how do you do that? You keep the first, change this division to a multiplication, multiply by the reciprocal. So that'd be 1 times minute over 1, which is just merely minutes. So the answer here is 2 minutes. Now, like I said, you probably read the problem and say, oh yeah, it'll take 2 minutes to fill that tank. You're absolutely right. But this is how you use your formula, use your equations, use the units, and the answer, T is equal to 2 minutes. Minutes a great unit to use for time. If you had come out with 2 per minutes, nope, something's wrong there. That's not a time, okay? So that's what we got. That's what they got, okay? Now, last time we went through these steps that were on page 12. Started actually on page 11. Now they go through some more considerations that will be, they say, may prove helpful. Some of these are actually, I think, better than the steps, but many of them just reinforce the steps. What they say is number 1 here, read the problem carefully, perhaps several times. Now we read it, and as I read it, I wrote down things as I was reading. They say make a sketch to help visualize and understand the problem in terms of the real world. If you remember Tuesday, we had the 2 masses on a table. I made a really ugly sketch of a tabletop and had the 2 masses on them. I don't know if that was helpful or not, but it helped me visualize what was going on. Okay? So read the problem, write down what they tell you is given, write down what you're looking for, like we said. How long? That meant what time. What time did it take? Okay? And draw a picture if necessary. Pictures are usually worth thousands of words, so use them. Okay. Number 2, be alert for information that is not stated directly. Okay? For instance, when we're talking about motion in the next chapter, when it says comes to a stop, they don't say what the final speed is, but you know what that means. If you come to a stop, that means your final speed is 0. Okay? So sometimes the information will be given one way, but you want to get it into a mathematical way. Final speed is equal to 0. Okay? And then the things like how far, that's going to be a distance. How long could be a distance. It could be a time. Understand that by the context. Okay? Now, sometimes they will leave out some things that you really do need, but they assume you know where to get them. And let me point out a few things to you. Now, I don't know if those of you who got the little books, when they asked me if I wanted to do those, I said sure, but I want the front inside cover, that table in that, and I'd also like the answers to the what they call the, they have a name for them at the end of the chapter. I'd like those included too. I know they haven't put the second one in there. I don't know if they put this or not. There is a wealth of information. It's the front inside cover of your book. Does the little thin book have these in there? Now, it may not be on the front inside cover. It may be a few pages in. See if you can find that anywhere. Here. What's that?
When you open the book, it has content and it has 1 through 7.
Okay.
And sheet 204. Then it starts going into the content. In the back you have the credit, the table of atomic weight.
Okay.
And all that good stuff. Basically like conversion factors, metrics, prefixes.
Yeah, this kind of things.
all that stuff.
Okay, that's where they are. It's in the back of the book then.
Yeah.
Okay, conversion factors, all this kind of stuff, and then metric prefixes, that's what you said.
Yeah.
There
Yeah.
they are. And then the
Periodic table.
physical constants, good for them. And then here's one other that's, I can't read it backwards. I can't read it, but whatever that is. And then the periodic table, fantastic. We'll be using that especially in the chemistry chapter. That's chapter 8. Okay, so good deal. I'm glad they put it in there. All right, so that's what they mean by sometimes they won't give you everything you need because they figure you can look it up in one of those tables. Okay, now number 3 here says understand the meaning and concepts that the equation represents. This is, I had to read this. They gave you the equation first. I said, well, what do these stand for? V stands for volume, T stands for time, K was your proportionality constant. They gave you that in the problem. Okay, we got it all covered then. Okay. What the equation does is represents the relationship that exists between the variables. These are the variables. The equation says how they're put together. Okay. Now, it says solve the equation before substituting the numbers. You don't have to do that. You can substitute first, but since they were looking for time, that was the unknown here, then we solve for time. And we did that by dividing both sides by k. Usually it's easier to do this way because that's represented by a single digit, a letter. If we had put 40 liters per minute in here in this equation, then you'd have to divide by 40 liters per minute. Divide over here by 40 liters per minute. Well, K is much easier to write than 40 liters per minute. But if you don't mind writing that, you can plug first. I call it plug and chug or chug and plug, whichever you want to do. Okay? But they like you to solve the equation literally with letters first. Note that whether the quantities are in the same units, and that's what I stopped and did before we plugged in to make sure these were in liters, those were in liters. This was in minutes, so our answer was going to be in minutes. The time was going to be in minutes. Okay? Then you perform the required operations. It was a division. Okay? 80 divided by 40 is 2. But don't forget to handle the units just like you do the numbers. The L's canceled out, the liters canceled out, and then just like you did numbers, when you had 1 over minute, you treated that like a division problem of fractions and made it 1 times minute over 1. That gave your unit to be minute, which is exactly what you would expect the time to be. How long? 2 minutes. Okay. Perform the mathematical, we already did that. Be aware that not all learning takes place in a given time frame, blah, blah, blah. I don't know what they're meaning by that, but you can read through that. Here's another example problem. Let's do this one. Now, I don't know if I should be on the same page or go to a clean sheet. Let's go to a clean sheet. Okay? Do you think this is helpful, or is this... Oh, I know what I'll do. I'll erase what's on here. Okay, I'm already on sort of a clean sheet. There we go. Mercury is a liquid metal with a mass density. Now, I don't know if you remember what our symbol for mass density is. That was rho. It looks like a P, but it doesn't have the serif up here, so that's a rho, Greek letter that really stands for our R, not that. The density of mercury, I'm going to put Hg because I know that's what mercury is. This helps me remember what I'm dealing with. The density is 13.6 grams per cubic centimeter. Okay. Now they say mass density, and for those who weren't here before, what mass density is mass measured in grams divided by volume measured in cubic centimeters. This could have been in kilograms per cubic meter. It could have been other things. It could have been a weight density, pounds per cubic foot. pounds per cubic yard, pounds per cubic inch. It could be tons per cubic mile. Okay, it could be anything like that. You wouldn't use that, right? Now, the next says, what is the mass of, so here's the thing, I'm going to write it out this time if I can find my pen. Where, there it is, okay. What is the mass, my writing stinks, okay, of 10.0 cubic centimeters of mercury? Going to abbreviate mercury to be Hg. That's what its abbreviation is. Okay? Now, the reason I wrote this out is look for the question. What is the mass? That's what we're looking for. If I could find my pen. The pen keeps disappearing on me. I don't know where it went here. There it is. Okay. So this says mass is the unknown. That's the question. Now, I come over here and they say 10 cubic centimeters. What in the world is that measuring? A cubic centimeter. That'd be a centimeter this way, a centimeter that way, and a centimeter that way. That's length times width times height. That's a volume. If I could find my pen. Where did the pen go? Oh, there it is. Okay. This is a volume. The volume is equal to 10.0 cubic centimeters. See, units are your friends. They tell you what the value is you're looking at or looking for. That's a volume, capital V. Little v we'll learn will be velocity. So capital V is volume. Well, here they gave you a density. I gave you that one too. Last time we discovered that the formula or the equation for a mass density, I've already said it once, rho is equal to mass per unit volume. We had that last time. Okay, since we're looking for mass here, that's the unknown, let's solve this equation for mass. Solve for mass. Get rid of anything except the mass here. Well, that doesn't mean erase it. This is divided by volume, so we're going to multiply by volume, but if you do it to the right side, do it to the left side as well. Here, volume over volume equals 1, so we have that mass is equal to volume times density. And the volume here was 10.0 cubic centimeters, and your density was 13.6 grams per cubic centimeter. And here's where units are your friends. Notice set cubic centimeters here in the numerator, cancels cubic centimeters in the denominator out, and you're left with 13 times 10 is 136 grams. That's the unit you have left. Now, for those who weren't here last time, this number here that they gave us is 3 significant digits. None of these digits are 0, so they're all significant. This one over here, if they had just put 10 centimeters without the point 0, that would have only been 1 significant digit, because usually a 0 at the end of a number is not significant. Unless, of course, it follows a decimal point, that means it is significant. So this is 3 significant digits. So our answer here, we don't go to the nearest tenth, we go to 3 significant digits. 136. Stop there. Don't put any more digits in there. Those are your 3 significant digits. And that's 136 grams. And how did the book do? They got the same thing. Good for them. I'm so proud of them. Okay? Aren't you? All right. That was our more math. Any questions on any of that? Okay. We'll be doing lots of problems and we'll set them up and go through. Maybe not in as gory a detail, but we'll hit those high points just about every time. Okay. So let's move on to, we've already done this slide, so we'll move on here. It just was convenient. Oh, yeah. It just convenient to use that slide. Okay, now we're ready for 1.7, the nature of science. That starts on page 13, bottom right hand column. Okay? Okay. Now, science itself, I don't know why this block here it fades in and fades out, but hopefully it's not too distracting. Basically, science, as we understand and know it today, only had its beginning about 300 years ago. Now, sure, there were some people that dealt with things like science way before that. Aristotle was a philosopher, and they called that natural philosophy, and it was much like science, but it's not quite the same as what we call science today. There were many others. Archimedes was an incredible scientist, yet he was way ahead of his time, we'll put it that way. Now, I'll say in the West it began about 300 years ago. China, I think they had stuff that would be classified as science for maybe thousands of years, okay? They were way ahead of us, okay? We just didn't know, and they didn't know us, so it didn't get shared, okay? But we count in the West that science began basically with Galileo and Newton. Now, they never met each other. Galileo lived, he died the same year that Newton was born, so of course they never knew each other. Galileo lived in Italy, Newton lived in England, okay? So they never crossed paths, except that Galileo did a lot of writing. Newton read every bit of Galileo he could get his hands on. So they worked hand in glove even though they never met, okay? Now, the ones I mentioned earlier, the ancient natural philosophers, and I guess that's what you would classify Archimedes, so he did a lot more than just thinking. He built things. I mean, he was an engineer. He was a philosopher. He was a mathematician. He was a thinker, big time. But the ancient natural philosophers only dealt with thinking through issues. They'd look at things, study things, and then think through it and say, this is what we think is happening, which was good. They were right on the money a lot of the time. I want to say most of the time. I'm not even sure it was most. A lot of the time, they were right on the money. Okay? But the difference between Galileo and Newton and those ancient philosophers were, starting with Galileo, he started experimenting. Okay? He would think through an issue just like the natural philosophers did. In fact, that was often his springboard. That was where he started with what they had written. He said, you know, I wonder if that's really true. Let's test it. That's the difference. The additional component here was understanding based on experimental evidence. Let's experiment and see if indeed that's true. See if it works. Okay? And quite often he found out it didn't. And let's go on to this. Here then is the scientific method. It was basically born with Galileo, perfected probably under Isaac Newton, and has been being used ever since. Now, it starts just like those ancient philosophers. They observe some aspect of nature. Study it. Think about it. Okay? Propose an explanation for what they've observed. Okay? That they did. And sometimes that got written into cement. I'm just kidding. And that became it. If Aristotle said it, everybody believed it because no one was going to argue with Aristotle. He was a brilliant, brilliant guy. Okay? That's where the ancient natural philosophers stopped. But where Galileo and later Newton and many others since then, they used the explanation they thought of to now, well, what if I did this? What should happen? If that explanation is true, then this should happen, right? All right. Once they do that, then they test, this is the big key here, test the predictions with experiments or more observations. Okay? So they start experimenting. they say, okay, let's do this. Let's see if this will happen. Okay. Now, if something surprises them and it doesn't come out the way that it was expected, then modify the explanation. And guess what you do then? Turn back around, make new predictions with the modified explanation, test those new predictions with experiments or more observations, keep the ball rolling. Keep the cycle going until you're pretty sure you have it figured out. Now, some things we'll never figure out, okay? I hate to use this because it's sort of a political flashpoint, but the theory of evolution, okay? That's going to be really hard to prove because can you go back and start with individual molecules and things like this and start building things? That takes thousands of years. Nope, don't think it's going to work. So therefore, it will remain a theory. It will remain something we're testing, we're observing, but we don't know whether it's true or not. Whether you believe it true or not, no one knows for sure. The Big Bang Theory. Hey, you can't go back and recreate the universe. You just can't do it. So there's no experiments in the world that you can go back and actually prove it, but you can get more and more and more observations, see if they mesh with what you were thinking. If they don't, modify what you were thinking, okay? So more of this. Now here's an example of scientific method. What are atoms made of? It's so bizarre they jump right into this, okay? Well, what we know, there's some tiny little nucleus that's in the center of that atom. And that nucleus is a net positive charge, okay? Flying around that nucleus is a cloud of electrons that are made up of negative charges. And if it's a balanced atom, electrically, it has the same positive charge in the nucleus as the total number of electrons flying on the outside. Well, what would be some things we could do? Well, let's take some material of some nature, collide these two atoms with each other, speed them up to high speeds, and make them collide with each other. See if you can produce some free electrons, knock some electrons off, see what we can find of the nuclei that are left, okay? Well, colliding two atoms yielded electrons. And when they really smashed them, they found protons and neutrons, which were what the nucleus was made of. So now they had a better idea. So atoms are made of electrons that fly around orbiting the nucleus, which is made up of protons and neutrons. Well, guess what? Let's try something else. Let's collide them at higher energy. See if we can break things down any smaller. This is how science runs. Okay? Now, let's get off of this really high esoteric thing. Let's think of, as if no one's thinking of it, the coronavirus. Okay? When it first came out, they were assuming, the scientists were, that it was probably a lot like some of the other SARS that's, let's see if I can remember what that stands for. Respiratory syndrome. Severe or severely acute respiratory syndrome or something like that, okay? They were assuming it was like SARS because it came from the same area that SARS came from other things. Well, they started testing some things and found, no, it doesn't quite act like SARS. Now, another early model was a lot like the flu. No, it doesn't quite act like the flu either, okay? Now, one of the reasons that they said, no, flu, is that quite often the people who got sickest from the flus were the very young people. Now, yeah, old people did too, but young children would get flu really badly. Well, guess what? The young children weren't getting COVID as badly as adults were. And young people weren't getting it as bad as older adults were. Okay? So it's different. Well, how do we, at first they thought Maybe it's done by what they call fomites that are on surfaces. So it lets everybody clean all the surfaces and things like this. Well, now it looks like it's more airborne, which is more like the flu sometimes. Okay, so that's why the mask. Early on, they didn't think a mask would be doing all that much good. Later, they found out, yes, it will. How did they find that out? More observations. Okay, my wife is an epidemiologist. She studies things like this. Now, her specialty is not coronavirus. She studies a virus called cytomegalovirus, CMV. But she still understands viruses, okay, or viri, however you say that, okay? Well, what they started noticing, now this is one example, but it really proves the point really nicely. They observed that one day somewhere, it wasn't here in Alabama, it was somewhere else, in a Starbucks. This was after they opened things back up and let people start coming in. Of course, all the people who worked in Starbucks had their mask on. All the people coming in had masks on. But of course, when you go to Starbucks, you usually buy coffee or some other drink, and quite often you'll buy some food to go along with it. And they may sit there and work on their laptops or their whatever. Okay? That's what Starbucks is all about, I guess. I don't usually go to Starbucks much, but that's what I hear. Well, this one guy came in, and the only place that was open was right by the air conditioning. I don't know if it was the return or the blower. I think it was the blower. Okay, that was the only place, so he sat there. Now, what he didn't know was he had contracted COVID and didn't know it. He wasn't symptomatic yet. He didn't have a fever. He wasn't feeling tired. He just went in for a cup of coffee or whatever. He sat there and worked on his thing. Okay, 4 workers had their mask on. Most of the customers did not have their mask on the whole time. He was sitting right in front of that. It blew the airborne particulates off of him, and something like, I don't remember the number exactly, something like 17 out of 23 people that were in the Starbucks that day when he was there came down with COVID. The 4 workers did not. And they said, time out, folks. Before that, they said the mask was mostly preventing you from spreading it in case you were the sick one before you knew you were sick, from spreading it to other people. Then they found that, hey, these masks also protect you from catching it from other people. So you see, science has evolved. Okay? Now let's go a different route here. They poured a lot of money into coming up with vaccines. Okay? And several companies are competing for it, and they're giving out the money for it. So these companies are going for it. Just recently, Johnson & Johnson had a very promising vaccine. They had one, as far as I know, significant bad outcome. They shut things down so they could study to see if that bad outcome was just a fluke or if it had something to do with the drug. Just like my doctor is doing with me. He wants to study my cells, the white blood cells, to make sure that the same markers that the drug I've been taking attacks that marker. If the disease has evolved so that it doesn't respond to that, he doesn't want to give me that drug anymore. He'll find another drug that attacks the marker that's stronger now. Okay? He'll also, so you see that science. He's always testing to see if anything needs to be changed. Okay, here is colliding atoms. I'm not familiar with that as much as I am my disease or other things. So I do know something about colliding atoms. So here are your general scientific activities. Collect the observations. The ancients did that. They did it really well. They observed and really observed and studied. They developed explanations. They did a great job of that. What they didn't do, and Galileo and Newton and people since then tested the explanations to see if they were valid, to see if they worked, to see if the predictions they made happen. Okay? Now, let's go to this process. Okay? That was the scientific method basically on page 14. We're now on the right-hand column of 14. Okay? Explanations and investigations. Most of the time they start with a hypothesis. Okay? A thesis is an idea. A hypo usually means proposed. Proposed idea, something like that. A tentative explanation for some observations. Okay, we see something happening. Let's see if we can come up with why it's happening. Well, let's see if we can develop an experiment that recreates an event or an occurrence to test that hypothesis. Now, I did work at the University of Georgia when I was in grad school in soil fertility. My major professor, that was his big area. Even though I wasn't in that, I was his grad student, so we did things like this. And one of the ideas at the time was one reason for poor corn harvest in a certain area of the state was that the pH of the soil, the acidity of the soil was too high, the pH was too low. So, if that was the hypothesis, that was the idea, we think this is why corn production is low. So what are we going to do? We're going to take a plot of land, okay, and we're going to try to have it as uniform as possible. Have the same type of soil, the same elevation, the same slope, much as we can the same. Okay? Now, we're going to split that plot of land into smaller pieces. Okay? And we're going to do this. We're going to treat that soil with all the fertilizers like nitrogen, potassium, phosphorus, calcium if we need it, whatever, so sulfur, whatever we need. We're going to treat all of that the same with these fertilizers, except for this. We're going to put no lime on this piece and maybe another piece over here and another piece over there. We'll put a certain level of lime on this piece, that piece, and that piece, and then we'll put a higher level of lime on this one, this one, this one, and maybe do that for 2, 3, 4 levels. Okay, what are we doing? We're testing, keeping everything else the same, trying to see if lime is really the problem. If it turned out not mattering what you did with lime, then lime wasn't the problem. It may have been nitrogen was the problem. It may have been phosphorus. It may have been anything. Okay? It may have been you had nematodes in the soil and that's what we're doing it. Okay? We just didn't know. So that's what our controlled experiment was. Comparing two situations with all the factors alike except one. So only the lime was different between all these plots. Only the lime was different. Okay? We mixed up where we're putting this so that any unknown variation there we were taking care of. So our control group is no lime, and then the experimental group was different levels of lime. Okay? We would do experiments like this, study the results, we'd make sure they all got the same amount of water, they all got the same amount of everything. They were all treated the same, except for that lime, that one influencing factor. And then, if indeed we showed great results compared to very lousy results, and at the same time we showed that no results gave you this, a little bit of lime gave you that, a little bit more gave you this, but more gave you that, it went down. That means we over-limed it. So we basically came up with an idea what the optimum amount of lime for that pH of that soil would be. Okay, that's just one example. Okay. Now this book gets into something they call pseudoscience. Okay, and before we get into that, they have a blurb at the top of page 15 on basic and applied sciences. Okay, science or research, they say. Okay, now here's what they're meaning there. colliding atoms, okay, that's basic research. What in the world is going on when this kind of stuff happens? What do we expect? What do we find out those atoms are made of? How are they related? How much energy does it take to break it apart? All that kind of stuff. Who's going to use that practically? I don't know, but it's basic research. Whereas how much lime is going to make a good corn crop, that's very much applied research. Okay, so that's the difference. That's what they're talking about here. They have several questions to discuss. That may lead you to a paper topic. So look it over. See if that's something you're interested in. Okay. Now, the pseudoscience that we've got on the slide now, that's over on page 16. Okay? Again, one of these slides covers several pages. Nothing is going to replace reading the book. I can't read all the, you'd be bored to death if I read them to you. Read the book on your own. Preferably before we go over it in class, but definitely while we're going over it and afterwards. Okay? But preferably do it before. Okay? What pseudoscience is, what the prefix pseudo means, is false. This is false science. Okay? It's almost like fake news, but I don't even like that term. False science. Something that looks like science, sounds like science, smells like science. You think it's science, but it's not. Not science. This is misleading and often, sometimes absurd claims of scientific results. All you have to do is go to the internet. You don't have to go there, but you could. You can probably find all sorts of stupid stuff on the internet that's absolutely absurd. No basis whatsoever. Okay. Well, here are some of the tests that they suggest, and these are listed on the bottom of page 16, right-hand column. Okay. Now, a few of the things, they've added one more from this one. The first one, what is the background and scientific experience of the person that is promoting the claim? Here they say the academic and scientific background of the claimant. Same type thing. Okay? If it's a Joe Blow you've never heard of before, he may be a brilliant scientist that you just never heard of before. But the odds are, if he's not, has some sort of academic credentialing, some sort of scientific background, you can trace where he studied, who he studied under, that kind of stuff, the odds are he's just pulling it out of his ear or some other unknown body part. Okay? Number two, what's the history of review by scientific peers? Now that sort of combines two of these. How many articles have been published by this person? So this goes back to his academic background and scientific background in peer-reviewed, and that's what this is talking about, scientific journals. And let me tell you this, okay, before anything is published in a scientific journal, it goes out to at least 3 experts in the field. Experts in the field. And they review that. They read it. They can sometimes be cruel in their critique of it, but they make sure that it sounds like it makes sense. And they're experts. They should know. Okay? So that's what they mean by review by scientific peers. Nothing gets published in a scientific journal without peer review. On the internet, anyone can put up anything they want to and act like it's total truth, and it doesn't have to have any basis in fact whatsoever. Okay. The next one says, has the person given invited scientific talks at universities and national professional organizations and meeting? That's what number 3 is talking about. Participation in scientific institutions and organizations. If they haven't been presenting at places where other brilliant scientists go that know the field and stuff, and they exchange ideas, they may clash sometimes, they may disagree sometime, but at least they've been in that environment that it's been tested. Again, peer review. Okay? Number 4, The claim published in peer-reviewed journal and independently validated by others. And that's what number 4 in the book. Has the claim been researched and published by the person in a peer-reviewed scientific journal, and have other scientists independently validated the claim? Now here's what that means. Some of these things up here, just a peer review, they just read it and say, no, that doesn't sound right. It looks like they have a flaw here, something like this. If it's a brand new, something that no one has done before, here's what else they do. They don't just send it by for others to read. They send it to some of the labs, university labs, national science laboratories, and they say, can you do this experiment? Because you see, to be published, you've got to have how you did it, your exact procedures. They call it, oh boy, I just had the name and I can't remember it now. Materials and methods. You have to tell what material you use, what method you use, the procedure you use, everything you do. That has to be in the thing. Then they send us to some respected laboratory and say, we'll pay you so much if you can reproduce this thing. They try to reproduce it. If they can't validate it, they say, nope, we can't get that to happen. We don't get that result. Or maybe they don't even know the result the other person got. They say, tell us what you find. They do it and they say, hey, we found this. And if it matches what the other guy found, then they say, okay, good. We'll buy it. We'll publish. So sometimes they actually have to independently validate some new idea. And number 5 in the book, they don't list here, does the person have something to gain by making the claim? Okay, in other words, is there some ulterior motive here that may be influencing, distorting his vision or her vision of something? Okay, so that's pseudoscience. I think they did probably too much here, but he likes to bring it up. Okay, now let's look on page 17 on some of the classifications they have of things. Okay, laws and principles. Now these are very, very similar to each other, but a little bit of a difference. Basically what they mean by a law is an important relationship observed to occur time after time after time after time. No one's ever seemed to refute it. Let me give you one very simple example. The law of gravity. Everything you throw up into the air is going to come back down, falling straight toward the center of the earth. Time after time after time. Okay? Now sure, we can fire a rocket into space keep adding enough energy until it escapes the gravitational field of the earth, and then it can go around the earth. Guess what? It's still being pulled toward the center, but it's not spiraling toward it. It's just that's what gets it in orbit. We'll talk about that later. Laws are usually descriptive in nature, which means they just describe something. Here's one. This is not me. This is someone whose last name was Charles. Charles's law. The relationship between the temperature and pressure in a gas. Okay, I'll give you a very simple example of that. When I was in grad school, my terminal degree was up in, I did in Lincoln, Nebraska. Okay, it was cold up there, folks. And there was a kid that went to our church, a family that went to our church. It was a woman and her 2 kids. The husband had left, moved into another town halfway across the state, and Nebraska's a pretty big state. So the boy didn't have a lot of male influence. He had his mother and his sister, and his mother was always trying to beg for some of the men of the church to do things with him, give him some role model, masculine role model. And I thought, hey, I'm single, I'm a grad student, what do I know about kids? So I didn't even think about it. Until he came out for this church softball team. Well, he and one other young guy were doing it. They were the only 2 high school students doing it, but they were very good athletes, and he did very, very well. So I was encouraging him, and we got along really well. I thought, well, maybe I can do some stuff with him. So I started doing some things with her. I went over one Sunday afternoon. It had just started getting cold, he had left the basketball out overnight, and so we're going to shoot some hoops on the garage basket. He went to pick up the basketball and it was flat. Not totally flat, but too soft. He said, "Oh, I must have punctured the ball. I better go pump it up." But he had left it out overnight, and like I said, it was cold. I said, "Just take it in the house and leave it. We'll do something else for a while." He said, "No, I need to pump it." I said, "Just do it." So he did. He took it in the house, left it there. It was nice and warm in the house. And then maybe an hour later, I said, "Why don't you go check the basketball?" He said, "Well, it's flat. Don't you remember? Go check the basketball." He went in the house and there it was, totally done. There's a relationship between the pressure and temperature of the gas. When it was cold, the pressure went down, it felt soft. When it warmed up, the pressure increased and the ball was nice and fully pressurized again. That's a relationship. It always happens, okay? It's descriptive in nature, okay, but it's observed time after time. Now, a principle is also descriptive in nature, but it's usually a little more specific than a law. Now, that's a weasel word. Usually a little more, yeah, but the difference is largely one of extent. For instance, some people call Archimedes' law of buoyancy, others call it the principle of buoyancy. It just depends on the extent, what you're talking about. There's not always a clear distinction between a law and a principle, okay? And this is one, Archimedes' principle relating objects, fluids, and buoyancy. Some people will classify that's a law, some people call it a principle. Here's one principle, okay? This is sort of fun, that's the only reason I'm going to do it. What do you think is going to happen if I blow underneath this piece of paper? You see how the paper is flopped there. Someone tell me what you think the paper is going to do. Anybody? If I blow on the paper. Anybody?
Your breath will generate lift.
Okay. Lift. Okay, I heard him say that. Lift. So let me see. I'm going to blow. Sure enough, the paper went up. Did y'all see it? Good. Okay. What will happen if I blow over the top of the paper? What's going to happen? Anything?
Not enough air going under, meaning you'll be pinned down.
Okay, let's take a look. What happened? It lifted again. What in the world is going on there? Okay. Well, Bernoulli, one of the famous Bernoulli family, it was actually Daniel Bernoulli, noticed this, and here's what he came up with. That the velocity of a fluid, whether it's a gas or a liquid, a fluid, the greater the velocity, the lower the pressure. Inverse relationship. Now, when I was blowing under the paper, of course I was giving it velocity, but it hit the paper and slowed down. Well, it hit the paper and pushed the paper up. That was one phenomenon. It really didn't have to do so much with the velocity as it did. I was adding more molecules to push against the paper. But when I blew over the top, I was taking the air, increasing its velocity, that reduced the pressure, and that created lift. Now, I don't know if any of you have ever driven a pickup truck before. I've had a few in my lifetime. Not all belonging to me. I grew up on a farm, so I grew plenty there. But we had a pickup at one time. And this is something you might notice. If you had something on the back of the pickup, driving down the road, picked up speed, things start blowing off the pickup. They just lift off the pickup and blow off, okay? I had a piece of cardboard do that, okay? I was taking it somewhere to the dump or something like that, and it just lifted off the truck and flew off. Why did it happen? Because the air going across the top of the cab was at a greater velocity than the air underneath it, so it picked it up and left it off. That's Bernoulli's principle, okay? That's a principle. Sometimes a little more specific than a law. Okay. Let's look at theories and models. This is on page 17, the right-hand column near the bottom. And these are talking about, let's see, in the book it says models and theories. Here it says theories and models. Okay, a theory is a broadly based set of working hypotheses, like the Big Bang Theory, the theory of evolution, any kind of theory you might come up with. Working hypothesis. Based on a considerable amount of experimental support, you just can't throw out a theory and make it out of thin air. You have to back it up. But you don't have enough to prove anything. It forms the framework for your thought exercises, your experimentation. That gives you something to work on. For instance, the theory that maybe lime limits the production of corn. Well, with that theory in mind, and you go into the biology of it. The acidity of the soil maybe damages the roots don't take in nutrients as well. That's what's doing it. Okay, so that's the theory. Test it with your experiments. Okay, now a model, on the other hand, is a collection of theories, not a collection of hypotheses, but a collection of theories or ideas intended to represent a physical system. Okay, oh, and by the way, have you ever used Bernoulli's theorem before? Any of you know that you have? Or is it brand new to you today? Say again?
Probably making paper airplanes.
You're right on the money there. If you've ever been in a real airplane, that's how airplanes fly. Because picture their wings. Their wings are bulbed like this in front and narrow down at the back. They have a little slant to them as well, but they do like this. What is happening with the airplane, the air over the top of the wing is going at a greater speed than the air underneath that gets slowed down by hitting against the plane, and that's what gives it lift. You use the term perfectly to begin with. That was lift. Air going over the top has greater velocity and therefore lower pressure until it lifts the plane off the ground. Because think about those planes fully loaded with passengers, what? Maybe 300 passengers or something, 120 passengers, something like that. All that luggage, all that steel or aluminum. I mean, it's a heavy thing. But what does it have to do? It goes down the runway, picking up speed all the time until it gets fast enough, and then it just lifts off the ground. That's Bernoulli's principle at work. That's how birds' wings are. That's what the Wright brothers looked at, how birds' wings were curved like that. A seagull, big wing in front, and it narrows into a flare at the back. That's how they built their wings for their aircraft. They were the first to get off the ground. Okay? That's exactly it. So people do use these. They use the models. Okay? These are useful for regimes that are either too small or too vast for direct observation. So let me give you an example of a model. Now this is a mathematical model, not a physical model. There was a guy when electricity was just being learned about, and they had discovered that electricity and magnetism, which had been known about for years, were related. They didn't think there was any relationship, and indeed they were. Well, this guy named James Clerk Maxwell thought through, I don't know how he did this in his brain, but he thought through and came up with a set of 4 equations. He may have had more to begin with, but they were condensed into 4. And they were partial differential equations. It's really heady stuff. And he proposed this mathematical model of how electricity and magnetism were related to each other. Well, when he proposed that, that was early on. They didn't have the technology to test it. So that was a model out there that no one knew whether it worked or not. Until probably pretty close to a century later, a guy named Heinrich Hertz finally had enough technological equipment that he could test that, and guess what? Maxwell's equations worked like a charm. It was a model that they didn't know whether it worked or not until then. Another example, one of the early chemists was named John Dalton, and he noticed that certain elements, atoms, always combined in certain ways. Carbon seemed to combine with a certain number of things, oxygen, say, or hydrogen, or something like this. Hydrogen does with oxygen, all these different things. And he got it down to, and others observed this too, the law of definite proportions. They always combine in definite proportions. Why? Well, his model was every atom had so many hooks on it. Carbon had 4 hooks, oxygen had 2 hooks, hydrogen had 1 hook, and he went through and did these things, and sure enough, H2O, water, oxygen had 2 hooks, hydrogen 1 and 1, that made H2O, water. Methane, 1 carbon, 4 hydrogen. Carbon dioxide, 1 carbon, 2 oxygens. Carbon had 4 hooks, oxygen had 2 each. Hey, it fit. Well, guess what? Even Dalton didn't think they were hooked together with hooks, but he used that as a model. Okay? Later they found out it was unpaired electrons. Those were the hooks. They weren't really hooks. They were unpaired electrons that combined and made electron pairs. But that was way before they knew enough to know what electron pairs were about. Okay? So that's why it says sometimes it can be a physical or mathematical model, sometimes based on sketches or analogies. Okay? Those atomic models, you can't ever see an atom and see what's going on in there, so it's way too small. Okay? And basically, electromagnetic theory, too small too. The Big Bang Theory, whatever that model is, too vast for direct observation. Little known scientist named, what was his name? Maybe Albert Einstein? Yeah, that was who it was. He came up with a theory that gravity actually bends. Okay? And people said, wait a minute here. But no one wanted to argue with Einstein. He was way too famous for that. Until there was a certain supernova or something that happened that they were able to observe, and sure enough, they observed objects in space that seemed to follow a bent gravitational field pattern. Never would have had it, but if he hadn't had the model out there that when the event came along, they were able to test. Now, I did a really poor job on that one because I don't even understand what went on. But yeah, that's what we mean by a model. Something way before maybe you're able to actually test it. You create a model saying, this is what I think is happening. Later, when you get the technology, test it and see if it does. Here's one example. I think all of us have seen a rainbow before, right? Why in the world do we see those beautiful rainbows? Let's make a few observations first. Well, they're going to show us a picture, so let's show the picture. There is a beautiful rainbow, okay? It's a double rainbow, one going here and one going there. Now, I'm going to tell you something, and the next time you see a rainbow, see if it's not true. When you see a rainbow, look behind you and you'll see the sun. The sun is always, always, always behind you, directly behind you. When you're facing that rainbow head on, the sun is directly behind you. That's one observation. Here's another observation. I don't know if you can see on this one, but you see the yellows are at the bottom and the reds are at the top. But on the second rainbow, the reds are at the bottom and the yellows are at the top. What is going on here? Now, another thing you'll notice, if you can picture the center of that rainbow, I don't know if it's showing here, and you had a sextant or something that you could do, this is a pretty level looking field here, and measure, you would see that first the rainbow is always a fixed degree from the center. The second rainbow is another fixed degree, and you see the difference maintains the same throughout the arc of that rainbow. Okay? And they're always the same. Those are your observations. What would be the I left off the obvious one. When do we see a rainbow?
After it rains.
After it rains, of course. Okay? the most obvious observation. You don't see them on a clear day like today, ever, okay? It's always after it rains. So let's put together several things here. First, it seems like little water droplets have to be in the air. Little, basically spheres of water, okay? Now here's some other things. We know that water has a different index of refraction from what air does. We know that, okay? If you ever stood in a pool and looked at your legs, they look shorter than they really are. You looked at an angle and they look like they're bent, or put a ruler at an angle into a thing of water like a jar or something like that, and it looks like it bends. Well, that's because water has a different index of refraction. It bends light differently from air, okay? So that those little raindrops, all those little raindrops out there, are both reflecting and refracting. Refracting means bending, reflecting means reflecting the sunlight with lots of individual droplets out there, okay? And here's what the model is. If this is a drop of a raindrop, approximately a sphere. Now, if the sunlight came in here, it's going to go out there. So you get basically no refraction, or not much refraction, and certainly no reflection. But at a certain place, when the sunlight comes in here, hits the raindrop, it bends just like it always does, that's the refraction, and splits the rain into a prism effect. Red on top, yellow next, orange next, then yellow, then green, then blue, then indigo and violet. Well, there's really no indigo, they put it in there so you can spell Roy G. Biv. They do that, they break it. But coming in at this angle, then it hits the back side of that water droplet and reflects. So it first refracts, the sunlight refracts, spreads out, okay? We know it does, a prism does that, okay? But it hits the back of the raindrop when it comes in at this angle and reflects. It's called total internal reflection. It happens at one specific angle, okay? And when it reflects there, then the colors flip on you, and when they come out, they bend again, just like they bent going in, they bend coming out, and the result is always 42 degrees. So if you had your sextants here and measured the angle to that rainbow, 42 degrees. Okay. Now, anything beyond here, it bends, but it doesn't get total internal reflection. Anything in here, it bends, but it doesn't get total internal reflection. It's only at that 42-degree angle. That's the only place that the light goes in, reflects, and comes back out. Okay. Now, but there is another place here, right at the very edge of that raindrop. It goes in and gets bent again and reflects once, but not just once, reflects a second time. Every time it flips its orientation here and flips it again, comes back out bent, that's a 51-degree angle. And if this is 42, that's 51 degrees every time. And that's the only place. Now the trouble is, oh, one other thing I forgot to notice. Which is the brighter rainbow? The inner or the outer? The inner. Every time. In fact, sometimes you'll never see the outer rainbow. It's just too dim. But when you do see it, it's always dimmer than the inner one. And here's why. Because very few sunlight rays hit at that because that's right at the tip. A lot of sun rays will hit here or down here at that same thing. You get more sunlight being refracted here and reflected than you do right down at the very tip and doing. And because of the second reflection that reverses the order, that's why this one is red, orange, yellow, blue, indigo, violet from the inside out. This one's from the outside in. red, yellow, orange. You can't make out the colors except you see the red down here and then more yellow at the end. That explains that model of the total internal reflection only at those two angles where it actually happens, and more of it happens at this angle, less of it at that one, because this is so little water to go through here. Sure enough, that's going to accommodate every observation you made. The reversing of the color, the fact the sun's got to be behind you because that sunlight has to be going in parallel. Anywhere else, not going to see it, you know. I mean, you can see it other places, but always going to be behind the observer. Okay. So forget about the leprechauns at the base of the rainbow. That's myth. Okay. Not even science. And I do believe that's the last slide in the chapter. Okay. They have on this page, I don't even pay attention to it much, concepts. This is on page 17, concepts applied seekers of pseudoscience. Why would they even talk about that? But they do, and it's worth a read. It's sort of interesting. They have some graphs here that basically model some of these modeling. Okay, if you can graph things and record that, that helps you understand what's going on. Okay. And there's a little science sketch there too. Here's a picture in your book of the model of the rainbow. I think this is even a better picture than that one. This is really brilliant, isn't it? Okay, if you got your book, you see it. Inner rainbow, outer rainbow, much brighter, much darker. Red's on top here, red's on the bottom there. The angle difference is always the same, and that's because of your model. Here's another. And this isn't in your on the slide set, but here's one. We'll talk about this in a later chapter. Somebody many years ago said, hey, look at the Atlantic Ocean there. Look how South America, Brazil pokes out, but the armpit of Africa goes in here. Could they have one time been together? Notice how the European coast slants this way, but the North American coast slants that way. Could they have fit together? Could they have been part of a bigger planet? Now, that concept was called continental drift. Okay? Someone proposed it. I don't even know if anyone has the name. I'm sure someone must have the name. But he was laughed out of the building. Okay? They said, you've got to be kidding me. Continents don't drift. You're just making things up. That's just coincidence. The shapes are like that. Continents are fixed in place. They can't move. Okay? Until now we have the technology, and now we have the theory, and we do know that the continents are drifting incredibly, incredibly slowly, but that's the basis of plate tectonics. Now that's replaced the concept of continental drift, that the earth is made up of plates, and those plates do move. Okay? But the guy who first came up with this, just based on his observations, no one paid him any attention at all. They laughed at him. They ridiculed him. Okay? So, another example of an observation, a proposal, hypothesis, but they couldn't test it well enough, and they made fun of him, probably kicked him out of the society. I don't know. I don't know the whole story. Now, I'll say this every chapter. I've already said it today. Nothing replaces reading the chapters. So please, folks, read your chapters. Okay? Now, on the next page, I thought I was through. Oh, yeah, it's on the page with the summary. Once you finish reading the chapter, at the end of every chapter, there is a summary. Now, some of these summaries are fairly short. This one's a little longer than it looks like because it goes on to the next page there at the bottom and a little at the top of even the following page. That's the summary. So it's a pretty decent sized summary for this short of a chapter. But usually before the summary, but here it's in the summary, here is a blurb on Florence Bascom. I think that's her name. Yeah, Florence Bascom. Okay. Most of the time, women aren't celebrated in science because they weren't even allowed to have education in the past. But she was an exception, a U.S. geologist, um, expert in the study of rocks and minerals, um, and she started the geology department at a women's college, Bryn Mawr College, very famous college. It goes into that. Guess what? If you choose to write on her, this may give you inspiration to write on her, but this can't be your source. Remember, your paper, you have to have outside sources. You cannot use this as your source. You can use this as a source of idea. Yeah, I want to find out more about Florence Bascom, but you can't use this as your source. You have to go outside the book, into a library. Internet, if it's reliable, remember, so much on the internet is total garbage. But in reading this, you might see other things that you might find interesting. Mary Holmes is mentioned, the first one to actually get a PhD in geology. There's just many, many things that these can give you ideas, but remember, you can't use this as your source. Okay, so after the summary, they have what they call the summary of equations. Now this chapter only has that one. That was your density equation. But you can write that density equation at least 3 different ways. I don't know if we did this in class, but let me do it now in case we didn't. I'll do it on this. Remember that density, we've used it this way, but I don't know if I wrote it. The density is equal to mass divided by volume. That's the mass density. But if you multiply both sides by volume, we did this before, you get mass is equal to density times volume. We solve one of the problems that way. Or if we divide both sides of this by density, you get mass over density is equal to volume. So here you solve for density, here you solve for mass, here you solve for volume. So anytime you have an equation like this, that actually represents 3 different equations. Okay, so even though they only list it one way here, that gives you 3 different equations. Okay, but it's really one principle they're talking about. Okay, and lots of things in physics will follow those kind of patterns. And let me give you sort of a nice little cheating mechanism. It's not really cheating, but let me clear this out of the way so I have more room to write here. It has nothing to do with model of a rainbow, but I'm just writing it here. Some people, and I didn't know, never run into this until I was in the Navy and taking some Navy schools, they used either a circle or a triangle. It doesn't matter which one. I sort of like the triangle better, but circles are fine too. And they take and do a horizontal line, which always means division. Something didn't come out very horizontal. And then a vertical line, which means multiplication. So I'll put the multiplication symbol there. A horizontal line always means division. Okay. Now, pick the thing that stands kind of alone. And when I had my 3 models there, remember the first one was density is equal to mass divided by volume. So whatever is on top there, that was the mass. And it was density is equal to mass divided by volume. Okay? You could do it over here in the triangle, same way. Put mass on top, density here, volume there. Okay. Now, what if you were to cover the density? Density is equal to mass divided by volume. Yeah, that's that one. But what if you covered the mass? Mass is equal to density times volume. That was the second one I had there. Or cover the volume down here, and volume is equal to mass divided by density. That's just a quick and easy way to remember these. If you get them in the right order to begin with, you got it knocked. So you can do all 3 formulas just based on either that circle or the triangle. Density is mass divided by volume. Mass is equal to density times volume. Volume is equal to mass divided by density. There it is. We'll use those kind of things over and over and over and over again in this course. So stand ready for it. Some of you I know, I bet you automotive students have already done Ohm's Law, haven't you? that works the same way, identical. Or the power formula works the same way. Lots of things will follow that pattern. Okay, so after that we have the key terms. And that's a pretty good list of key terms there for such a short chapter. Now they are listed alphabetically, but after the listing they give the page numbers where they're either defined or described. And you'll find a lot of these key terms here are in your summary in italics, so you can sort of cross-reference. But in most chapters, maybe not this one, but in most chapters, the very best thing to study for your test are these concepts, applying the concepts. These are multiple choice questions, and they go on to the next page, I think, and the next page. There's a total of 44 multiple choice questions here with answers given. There at the end, answers are given, and that's usually the very best thing to study for your test. Okay? Now, the first test is different from most other tests because the test bank just has such ludicrous, nitpicky little things they had in it. I took their questions and made them into something a little more reasonable. So there's probably more calculations in this first test than you'll find in the other. First test is one page. I think it's only like 10 questions, but several questions have multiple parts to them. So it's a total of something like 18 blanks or something like that. So everyone doesn't count 10 points, you know. It's every blank counts, and so it gets spread out a little bit more. So that's going to be, so know that formula and be able to use it in any way, shape, or form that it's given. Okay? If it's asking for volume, figure out how to use the volume. Pay attention to the units. Units were important here. Okay, so that's what the first test is going to be. The subsequent tests for chapter 2, 3, 4, 6, and 8 will all be mostly multiple choice, like these concepts questions, but occasionally fill in the blank or simple solutions, okay, mathematical solutions. It's a lot different from the people who had 111. Those are almost always totally multiple choice with a few fill in the blanks. These will have a few that have solutions to them. You actually work out problems. The first one, several like that. Subsequent ones only 1 or 2 or 3 or something like that. But the rest of the test will be more like the 111 test. But you will have questions. Okay, then after that you have questions for thought. Starts on the one page, and oh no, this is the shortest group of questions for thought you'll see. 10. Most of the time there's like 16. But then they have for further analysis, there's 7 of those. Most of the time there's only like 4 or 5 or maybe 6, but not 7. Okay, and then what they call the parallel exercises. These are like the examples they give in the book, and this is what I asked them to put the answers for the part A in the back of the book. They're in this thick book. I asked them to do that for the thin book. That's the thing they didn't do, I don't think, unless they came out with a new edition of it. So that's your chapter 1. We've got about 15 minutes before we start chapter 2. I'm all in favor of taking a little break here. Are y'all in favor? Okay, so I'm going to put the recording on pause. Okay, that pretty much finishes. Now, is anyone out there? I don't want to be talking to myself there. Is anyone back yet? Anyone?
I'm here.
Okay, good. All right, glad someone's there. All right, so what I'm going to do is get out of, well, I can't get it to advance. Get out of chapter 1 here. Ooh, that was loud. And we'll discard that. And we'll move to chapter 2. Now I'm going to move. Jacob, you're in the way. Okay, there we go. I'm going to cancel out of chapter 1. And I do not see chapter 2. It was here. I had it open. So let me go back and open it again. Oh, here it is. I bet you it's here. There's chapter 2. Okay. So I need to get my, have to maneuver these things around. The screen share again. Now we got chapter 2. Okay. Now I have to move things around. Y'all can't see this, but I have a toolbar that blocks a big part of my screen here. Move that out of the way. I think we got screen share up again. And what I'll do here is go from current slide. Okay, can y'all see chapter 2 here?
Yes, sir.
Okay, good deal. Okay, chapter 2 is talking about motion. Okay, and the picture in your book are some hot air balloons. There are some other hot air balloons, both of them very beautiful pictures here. Here is the core concept, also on page 25, and it says a net force is required for any change in a state of motion. Okay, number one, we haven't even defined what a net force is, what we mean by net force. Okay, any change of a state of motion. We really don't know what we're talking about there either. We sort of have a concept, but there's the core concept for the chapter. We got a lot of building up to get to that, so let's get started with that. And a good place to begin is, what in the world is motion? Okay, so here's basically how the chapter is split up. We're first going to describe motion in the first approximately a third of the chapter, not quite, but something like that. Then we'll explain motion. Why does motion occur the way it is? And this basically will deal with Newton's 3 laws of motion. This is describing motion, this is explaining motion. Then the last part of the chapter is going to talk about some applications of motion, including a concept called momentum, including other things like gravity and things like this, circular motion. Those kind of things will be talked about toward the end of the chapter. So we'll start with, describing motion. I'm so sorry, I'm going to blame it on my anemia. I just start running out of gas late in the day, so hold on. Pump a little sugar and caffeine in there and see if that will get me going again. So we're going to describe motion. There are 3 basic concepts that describe motion. And the first of these has really very little to do with motion until you really think about it. It starts with position. Here I am right here. What if I want to go to here? Well, I have to define my position here and my position there. You've got to have a change of position to have motion. Okay, so that's where we start, position. Now, how do we measure position? Well, one thing we could do is distance. How far this point is from that point. We would answer that with a distance. A little bit better way to answer that would be displacement. Okay, now that sounds like the same thing, and in everyday use of language it is the same thing, but it's not quite in physics. Here's what we mean. The displacement from here to there is not only how far we traveled, but in which direction we traveled. So displacement has both distance and direction, whereas distance is just a number, how far. Okay. Now, these next 2 words, almost the same. If you know your change of position, and basically when you talk about motion, things are changing. Okay, you can't have motion if you're in the same place. You got to be moving, you got to be changing, you got to be moving. So if you're moving and changing your position, that takes a finite amount of time to do so. So if you combine displacement, which maybe you'd measure in distance unit, feet, miles, meters, millimeters, centimeters, kilometers, furlongs, whatever you're measuring your position in, divide that by time and you get your speed. Speed is, again, how fast you're traveling. Velocity which we use in everyday English as if they're the same. In physics, they're not. Velocity has direction associated with it. Speed does not. Speed is how fast you're traveling. Okay? Velocity is how fast you're traveling in a given direction. Okay. Now, what happens if you change your speed? What do we call that in a car if you change your speed in the car? What pedal do you push? Accelerator. So a change of position is a speed or velocity. Actually, a change of displacement is a velocity. A change of velocity is an acceleration. And that's what your accelerator does. And believe it or not, so does your brake. Because your brake goes from one speed to another speed. Change of speed, that's a negative acceleration. Okay, we'll talk about some others later. So what are some applications of these descriptions of motion? Well, we're first going to talk about horizontal motion. It says on land, it doesn't matter where you are, horizontal motion. One-dimensional horizontal motion. Okay? Then we'll talk about vertical motion. Okay? Falling objects. And then the third application will be compound motion, where you're changing horizontal displacement and changing vertical displacement too. Any of you baseball players? Okay? When you hit that ball, it goes up in an arc and it comes down, unless it's a grounder, of course. But if it's a fly ball, it goes up and comes down. Basketball players, you throw it up, it comes down. Okay? They always follow arcs. Even those firing quarterbacks throwing those bullet passes, they still are following an arc. Okay? They always do. That's compound or two-dimensional motion. Horizontal and vertical combined, and that gives you two-dimensional motion. Now, let's go back to the three motion concepts. Okay? The basic idea here is that and here they're introducing forces way ahead of time, but, I'm sorry. This is the second, okay, sorry. What is motion? Description of motion, explanation of motion, application of motion. This one talks about those describing motion. We'll come back to that in a minute. The second of those was explaining motion. The basic idea here, you have forces, you have inertia, we'll talk about what that is, mass, well, that doesn't have much to do with motion except how you describe it, and then, like I said, there's Newton's three laws. Then the third thing was the applications. Momentum and impulse, they're very closely related. Circular motion, like planetary motion or others, and Newton's law of gravitation. And then kind of combining these two together, we can talk about the Earth's satellites. And that will also involve some momentum examples as well. Okay? So that's the overall concept of the chapter. Let's go back to the very beginning when we talk about motion. And when we talk about it, we're going to talk about how we measure it, because that's what physics is all about, measuring your quantities. Okay. Like we already said, two fundamental components. We said there are three principles, but two components: distance and time. Change of position, that's your distance. Change of time, that's how long it took you to change. Now, I don't know if any of you were the old Star Trek fans, and beam me up, Scotty. It was almost instantaneous. You went from one place to another, but even then, it took a finite amount of time, no matter how far they were traveling. Okay? So anytime you have a change of position, it's going to take some finite amount of time for it to happen. So we put those together like this. Okay? Here we have, and I can't see it because this thing's in the way down here, but I don't know if that's bothering you. Here we have a distance. You started at the zero distance. You went 1 mile, 2 miles, 3 miles, 4 miles. Every mile you took a minute to get there. 1 minute between the first and the 0 and first mile, 1 between the first and second, 1 between the second and third, 1 between the third and fourth. So each one of those took a minute. Okay? That was your time. This was your distance or displacement, change of position. Okay? That's how we define motion. If that car was sitting still, no distance traveled, and no matter how long you measured the time. Okay. Now, just for fun, it has nothing to do with what we're talking about. If you're going 1 mile in a minute, how fast are you going on your speedometer? 60 miles per hour, because there's 60 minutes in an hour. If you went 1 mile every minute, that was 60 miles per hour. So that's moving along pretty fast, okay? That's not in town. Hopefully, you're going to get a ticket if it is. Okay. Let's see if I can figure out where we are now. We're just about to introduce the concept of speed. So let's stop right there, and that's where we'll end the day. And somehow I've managed to lose my pencil. I had a pencil here on the desk all day today, I think. Maybe I didn't. And oh, there it is. I moved it over there. So we'll pick up, well, it's already marked. That's where we'll pick up next time. Okay? So measuring motion, page 27 with speed. Okay? This will be our slide. All right, I'm going to put the book aside for now. And now I'll go on and close out this. Okay? And close out this. Okay? Now let's go back to the courses on Google Chrome. Okay? That's what I'm using. Let's go to Physical Science 112, where we were, and we'll go down to the weekly assignments and activities. Those who weren't here to begin with, I was showing this. Go down to, oops, we open weekly. Now, Brianna, you're in the way, so I'm going to have to move you up here. You can't see, but okay, I've got to open weekly assignments and activities. And we're going to week 1 first, because that's where we are right now. Yeah. Goodness gracious, this thing keeps moving in the way. I'm going to move it out of the way again. Okay. Week 1. All right, there we did. Now, I talked about the overview and weekly to-do list. We talked about doing Lab 1, but it's located in instructional materials. Lessons, PowerPoints, videos, handouts, and so forth. That's where your labs will be. So I'm going to open this up. If it opens, here it comes. Now remember the lab down here. You have to scroll down to see it. Here is the PowerPoint. I'm not the PowerPoint, the Word document. That's what you're going to be filling out to turn in. The questions are here, the blanks are here. Okay, we'll be working through this. I hope some of you have printed it out already. If you haven't, you can just write the answers down and send me the answers, or you can print it out later and fill in the answers, whatever. Here's where we're going to get the virtual lab. This link that you see right here, https PHCT Colorado edu, University of Colorado. So I'm going to click on that, and this is at the top of your lab too. Go to the Blackboard page for the course, go to course content, scroll down to weekly activities and week 1, instructional materials, lab 1, click on the laboratory simulation. That's what I just did. Now, I've got to move y'all out of the way again. So, Brianna, get out of the way again. Okay. Now, you see here on this page, it says simulations. When you get close to that, it opens up all the different kinds. We're doing physics now. So I'm going to click on physics. And when it gets to physics, now I got, maybe not have to move you out of the way again. Here's a whole bunch, 106 different simulations here. We're going down to the one that says density. So scroll down, they're alphabetical. There's the A's, the B's, lots of B's, the C's, 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 D's. There's your density one right there. So I'm going to click on this one. Now you'll see that different ones of them have these different symbols. This is a flash simulation run in flash enabled browsers. If you don't have a flash enabled browsers, you may not be able to run it, but you may be able to load the browser. Let me see if I can get that again. Yeah. And these will only be available through 2020. So we can still do it, but when I opened it before, I had to load the browser. So I'm going to open here, or click on that, then go up here to the circle in a triangle, and you'll see that's on your lab too. Click on the triangle, which is going to open it. Now it says at least Flash Player 8 required to run the simulation. No Flash Player was detected. Attempt to view the simulation anyway. Oh no, here it says get Adobe Flash Player. So that's what I'm going to click on. So here it goes. Now it says PHE Colorado wants you, that's Physics Educational Tools, something like that. Colorado wants you to run Flash. So it says Flash Player will no longer be supported after December 2020. We're still in October, so we can do it. So I'm going to say allow. Okay. And now it's loading. So here is the lab. Now I'm going to have to move y'all out of the way again. Okay. Y'all can't see this, but I have your names here. Okay. Yuck. I think I'm going to have to move you to the bottom of the screen for now. Okay. Let's see how that does. Okay. That's a little better. We're not going to use this one. This is your custom. But it does show some things that you may be interested in. If you measure the block of wood, 2 kilograms, and divide by its volume, remember density is mass divided by volume, 5 liters, that would be 2 divided by 5 is 0.40 kilograms per liter. Okay, and you can do different substances, and well, I thought you could. Okay. Oh, here is where you change it. You change it to styrofoam. That's going to really float. It's only 0.15. It has a mass of 0.575. We're not doing this. Don't write in anything yet. But that's what this one does. It gives you everything there. So that's not very helpful to us. So let's go over here to the upper right and click on same mass. Okay. And now we have 4 blocks. Okay. Now, it said record the mass of all 4 blocks. They all 4 have the same mass, 5.00 kilogram. So that's pretty simple, right? Just record that. Write it in the blank. Okay. Number 2, record the initial water level. That's 100 liters, 100.00 liters. Okay. I just started with the big block here. The yellow block, I said, place the yellow block under the water. Now, if you just put the yellow block in the water, it's not going to go underwater. You have to actually click down and hold it underwater. Okay? We know that it's 5 kilograms, but notice how, and I can't point to it without doing that. Notice over here, though, what the water level is. 110 liters. Okay, so that's what it says to do next. Place the yellow block under the water, not in the water, under the water. Record the new water level, 110 liters. Do you see what's happening there? Before I put the block in the water, it was at 100 liters. Now it's at 110 liters. So this 5 kilogram block took up 10 liters of water. Okay, so the number 4 says calculate the difference between what it is now, 110 liters, and what it was before I put it in the water, 100 liters. That's just a subtraction. Okay, So calculate the difference. Think y'all can do that, right? Anybody? Okay. What you get? Difference between that and that. 110 there, 100 there. What's your difference? Be bold.
890.
Okay, no. What's the difference between 100 and 110?
Oh, we got 10. I'm sorry.
10 liters. Okay. So you had a 5 kilogram block that displaced 10 liters of water. Okay. So now the thing is, number 5, calculate the density of the yellow block. Now you got a piece of paper there or whatever you're doing. What is density? Mass per unit volume. Now notice they're not using cubic centimeters or liters or anything else. Well, they're using liters, but not, okay. So it's 5 kilograms of water divided by your 10 liters of 5 kilograms of yellow block divided by 10 liters of water. 5 divided by 10 would be what? Second, 5 divided by 10. Kilograms divided by liters. Kilograms per liter. Units are your friend. Pay attention to them. 5 divided by 10 is? Anybody? Use your calculator if you need to. 5 divided by, second, 0.5 or 1/2, whichever you want to do. 0.5. Now, this has 3 significant digits. This has 5, so round it to 3. That would be point. That first 0 doesn't count, okay? 0.500 kilograms per liter. Okay, I don't think it's going to let me write on this slide. I'm going to try to, but I doubt if it will. So
it's 0.500 kilograms.
It's 0.500. Okay, I usually put a 0 in front too. You don't have to, but that is 0.500. Oh, Daniel must have had to leave and he's come back. Okay, good deal. All right, let's place the blue block in the water. Okay, whoops, don't bump into yellow. Okay, if you just drop it in, well, let's see. I tried to, oh, if I release this, oh, I don't have to hold it down, do I? What was its difference? Before we put it in the water, that was 100 liters. Yes, that's 5 liters. So what's its density? 5 kilograms divided by 5 liters is 1 kilogram per liter. That's why it really would hang right near the top, but it shows that it's sinking. Okay, so that's 1 kilogram per liter. 1.00. Keep 3 significant digits. What is the next one? The green block. Okay, I have a feeling that one will sink too. Yep, it did. So what's its displacement? Before I put it in the water, that was?
2.5 liters.
Yes, 2.5 liters. Okay, so what would its density be? 5 divided by 2.5. What would that be? 2.00 kilograms per liter. All right, pull that one out of the water, and let's put the red one in. What is its displacement? 1.25 liters. What is its density?
4.
Okay, it may be. I haven't done a calculation. It's 5. Whoops. I need to log into. Okay, I have to log into my phone first. I was doing it there. What did you say it was? 5 divided by 1.25? You're absolutely right. That was 4.00, need 3 significant digits, kilograms per liter. Always put your units. Units are your friends. Don't leave them alone. Okay? So, that gets us through. That was the purple block. That gets us through lucky 13, right? No, that was the red block. I called it purple there. It's up here above water, it's red. Okay, so that was the red block. Calculate density of the red block. You got it. Now, on the upper right, let's click on same volume. Okay, now these blocks all have the same volume, but they all have different masses. Okay, so we're going to start with the red block over here, and we're going to record the mass of the red block. What is the mass of the red block? 2.00 kilograms. Okay, that's number 15. Okay, number 16 says hold the red block underwater and record the new water level. If you just try to, get out of the way, green block. Okay, let's put the red block. If you just drop it in, it's not going to go under. You have to hold it under. Okay, and what's its displacement?
5.00 liters.
Okay, what would be its density? Two divided by 5, right?
Yeah, I was trying to do it in my head.
Okay, you can do it there.
2.5.
No. 2 to
4.
0.4, absolutely. 0.400. Okay, you need 3 significant digits, kilograms per liter. Okay, so there's red block. Okay, record the mass of the green block. See it? 4.00 kilograms. Yeah, 4.00 kilogram. Let's put it in the water without knocking the red one in. It's not going to sink, so we're going to have to hold it underwater. What's its displacement?
5.00 liters.
Okay, so then what's its density?
Uh,
0.800. Perfect. Kilogram per liter. Excellent. Y'all are getting this down really well. Okay, is it blue block next? Flip the page. Okay. No, we've calculated the green block and we stopped. Okay. And the reason I stopped is I wanted to hold it to 2 pages, and I wanted to get to mystery. Okay, so let's now click on mystery. And we have 5 blocks. We don't know their mass. We do know the original displacement of water. That's what it's always been. But we don't have the mass and we don't have the displacement. So what I'm going to do to say black, yellow first. I said yellow. So let's place the yellow block. We first need to put it on the scale so that we can determine its mass. So move it over here to the scale and put it on the scale. What is its mass?
65.14 kilograms.
Okay, now we have 4 significant digits there. Write them down. We may not use them all, but we're going to write them down. 65.14 kilograms. Now take that yellow block and place it. Let's see if we can put, oh yes, all we have to do is drop it in the water. What did the water level do?
3.38 liters.
3.38 liters. Okay, now those are things I can't do in my head. Okay, now I didn't write down, what was your mass?
65.14.
65? Is that what you said? Okay, let me go back. I didn't write it down. I'm not going to write it down, but whoops, I went off the scale. Yeah, 65.14 kilograms. 65.14 kilograms. Okay, and we're going to divide that by the, let's go let that splash. There it goes. 3.38 liters. Right, okay, wait, I just messed up mine. 65.14 divided by 3.38, 19.27. Excellent. Only thing is, I think we can only go to 3 significant digits, because you see the difference here was 3.38, 3 digits. Even though this one was 4 digits, we have to go with the least number of significant digits, so let's call it 19.3. Okay, now what I forgot to put on your scale, and I think you've got plenty of room to write it, especially if you're just writing on a piece of paper, let's show the table. See the show table here? And now ask yourself, what was that material? Gold. Hey, take that one and go home with it. Okay, boy, you had, how many grams of gold was that? That was a lot. You're a rich person now. And it's even the right color almost. Okay, so somewhere on your page there by the yellow block, calculate the density of the yellow block, you got room to write gold there. You see how that works? Okay, is it blue block next? So let's take the blue block and put it on the scale. And what's this mass?
0.64.
Okay, 0.64 kilograms. I'm going to go on and put this on my calculator. 0.64. Okay, I'm going to take that, and I'm going to try dropping it in the water and see what happens. Whoops, it floats, so they're going to have to hold that one underwater. What's its displacement?
1.00 liters.
Okay, so what is its density?
It's going to be 0.64.
0.64 kilogram per liter. You're good. Okay, let's show the table. And what have we got there?
Apple.
I just ate that for lunch. Okay, so we have an apple. Okay. All right. Let's go with the green block. Is that the next one? I believe so. Yeah. Now what I'm going to do is move these two out of the way. Oops. Get out of the way. Now I can't move it. Okay. So I'm going to just move this one since they don't seem to mind. I will just do this. Put it on the scale. What's the green block?
4.08 kilograms.
4.08 kilograms. Okay. I'm going to close my table. It's in the way here. There we go. So 4.08 kilograms. Now let's see if I can just drop that in the water. Nope, it floats too, so I'm going to have to hold it underwater. What's its displacement?
5.83 liters.
5.83 liters. Now both of those are 3 significant digits. Whoa. What was that? 4.08? I had it on. What was it? What was it? 08. Okay. I had it on my thing and then didn't realize. My calculator's messing up. I'm messing up. Okay. 4. Did it again. I did it a third time. 4.08 divided by, that time it worked. And what was my displacement? 5.83.
0.83.
And what did you get?
0.70.
Okay, that rounds, well, let's see. Since we have 3 significant digits for both of those, let's make that, and you're absolutely right, it would be 0.699. Look to the right. It's an 8. That rounds the 9 up to a 0, so you're right. 0.700. 3 significant digits, okay? And let's see what that is. Show the table.
It's gasoline.
Gasoline, you got it. Okay. All right, let's take that cube of gasoline out of there. I don't know how they managed to do that. See, I can't get it far enough. So, oh me, my E fell in the water. All right, what is next? Oh, no,
BD.
D was the red one. Okay, let's pick that up and put that on the scale. What you got?
3.10 kilograms.
Yep, 3.10 or 0.1. We're going to divide that by, let's see if that one floats or sinks. Ah! Oh no, what does it do? It does float barely, so let's hold it under. What's its is volume?
Mine shows 3.38 liters.
That's right, so let's divide by 3.38, was it? 3.38. And what do you have?
0.917.
Okay, 0.917 kilograms per liter. Let's get the table and see what that could be. I have an idea.
I forgot what I said.
0.917 is what you said, and that rounds to
would it be water?
not
Ice.
ice. Yeah, okay. And ice will just barely float, right? The only substance I think known to man, or at least naturally occurring substance, whose solid form is actually less dense than the liquid form. And there's a very good repercussion of that. Okay, so there we have that. I'm going to move this D out of the way over here. I think that's okay. And we'll finally put purple E here. Oops, got to put it on the scale first. What do we have? Okay, and we'll divide that by its displacement. Let's see if this is going to sink or float. Oh boy, did that ever sink. And what did its displacement? 1. So what's that density going to be? 3.53. Let's get the table and see what we got.
Diamond.
Oh my goodness, let's hang on to that one. Okay, that will be diamond. You're absolutely right. Okay. Any questions on the lab? That was way too easy, wasn't it? In fact, it was way too short, wasn't it? Do you think your computers would have done this on their own?
No, mine would have struggled.
Yours would have what? Struggled? Okay. Yeah, it could be because you had to load the flash player if you didn't have the thing to do it. That's why I did it here, and that's why I'm recording it, so it will be out there even for those people who didn't show up today. Okay? Have you got any questions on the lab? Does this help you understand density?
Yes, sir. It did.
Okay, good deal. I'm trying to find the sheet. Oh, I know where it is. It's here. Okay. Now, before we leave, I do want to say this. Does anyone have any way of getting in touch with Thomas Abrowski? He was in one of my classes either spring or summer. Do any of you remember him? You may not have been in his class. Also, Gerald Jordan. I don't think I've ever had him in a class. If any of you know him, please get in touch with him. Now, Rucker's not here today, so you two other GM guys, let him know what we did and where to go to see the lab, or how to do it on his own or whatever, so make sure he gets it. Brianna, I hope, is still here. Diana, I think, is still here. I hope so.
Here.
Good. Sharonica, I haven't seen yet. I think she's been in the class before, but I'm not sure she ever stayed in the class. So if any of you know her, be sure you let her know. She needs to do, any of them that are not here today need to do their course syllabus agreement. If they don't do that, they're not going to be counted present for this week, and they will possibly be removed from the class. Daniel is here. Rodrigo is here. Amia didn't make it in today. So let her know, if any of you know her, let her know how to do the lab. The rest of you are either here or were here last time.
Mr. Fowler.
Yes.
So I have to do my syllabus again as well?
Okay, several people are talking at once. I couldn't hear.
So I have to do my syllabus again as well?
You don't have to because you've been present, but it's always a good idea to do it. They really like to have everybody do the syllabus agreement. This is a different syllabus from 111. That was covering one thing. This is another. Okay, that was astronomy, earth sciences, and that kind of stuff. This is physics and chemistry. It's a different syllabus. So yeah, if you'll do that page, you don't have to do the fancy thing they say to do unless you find that easy to do. You can do it that way, or you can just take a picture of it, send it to me, extract it from the syllabus and email it to me, whatever you want to do. Okay, but yeah, everybody's supposed to do it. The thing is, it's not crucial for you, it's for the people who are not here. Okay, Valerie didn't make it today, which is really unusual. I had her in the summer. I don't think she missed a single class. There were a couple times she thought she was going to have to miss, but she didn't. But Dre's here, Tobias here, Leon's here, Jacob's here. Amia didn't make it today. But they've been here. They don't have to sweat it. Except they weren't here to do the lab together, so they're going to have to figure out or watch the YouTube video to see how to do the lab. Okay, now, after we log off today, I'll be posting your first test. So be ready to see that. It will be under Blackboard Messages. Okay? Now, it'll take a little while for me to get around to doing that. I don't know if my wife's home yet, but if she is, we're probably going to have supper first, and then I'll come back up and try to get the test posted sometime this evening. And I've got a bunch of stuff to do with my friend's death too, so it depends on how many phone calls and other things I get that rob my time. So any questions, issues, concerns?
No, sir. I'm good.
All right.
Oh, yeah. So I was asking you earlier about the book. You said something about McGraw-Hill.
Okay, this book, the publisher is McGraw-Hill. It is not Cengage. So your Cengage Unlimited doesn't work for this book, but if you're in a course that does, I think it's called Course Connect or something like that, that's the McGraw-Hill feature. If they have the same deal Cengage Unlimited does, then you can probably get your book through them.
So I have to purchase the book through McGraw-Hill.
No, you can buy it through the bookstore. You can buy it online somewhere. You can get a used book. You can rent the book. That's pretty cheap. You're not going to need it after this term, I don't think. So you have many ways you can go about doing it. That's up to you, but I definitely think the book is helpful. Those of you who were in 111, did you feel like the book was helpful? Yay or nay? Yeah, I think so. So you can't get it all from me in the PowerPoints, I don't think. So by all means, I'd say get the book somehow or another. Find someone who had it last term. See if you can borrow it or buy it from them. Okay? Some way, get your grubby hands on the book. Okay? Any questions? Okay, now do you feel like I've cheated you out of your tuition dollar and you want to continue in chapter 2 now?
No, sir.
Oh my goodness. What in the world? That shocks me. I thought for sure you would say, we want our dollar's worth. Okay, so since you said that, I guess we'll have to let you go. Any questions before we leave?
No, sir. I'm good.
Okay, so I'm going to stop sharing. I'm sick and tired of sharing. Okay, somebody has a question there. Okay, and I'm going to end the meeting for all of us, so take care. Folks, be safe this weekend. I know it's beautiful weather, real temptation to get outside and get with friends. Hey, be careful. If it can happen to Nick Saban, it can happen to anybody. Every time I saw that man, he had his mask on, fully right correctly, and he still wound up catching it. So be careful, folks. It's out there. It will get you. Okay?
Dude stood next to an air vent.
Say that again?
Man, dude stood next to an air vent. What can I tell you?
Is that all that happened? Wow. Oh yeah, the guy in Starbucks. Yeah, it can happen when you least expect it. Seems like even someone in the government has gotten it, haven't they? Never mind. We won't go there. All right. Let's take care. Be safe. We want to see you next week. So I'm going to end the meeting unless there's any objections. Any? Okay. Take care, folks. Our people are already leaving. Bye-bye. See you Tuesday. Bye-bye.